Hi everyone, welcome back. Today we are on lecture 14 and we will introduce a new topic called dyadic Green's functions. You will see what they are, where they come from and what they do. It's going to be slightly more mathematical than the previous lecture, but nothing too hard, and we'll see why. Okay, so what's the big idea here, right? So, half of this class so far has been on kind of trying to solve Maxwell's equations, and we showed that you can start from the sources, which is the current and charge distribution, and then from the currents you can go to potentials, and then from the potentials you can go to the fields, right? But that's kind of a cumbersome process when you want to do it numerically or computationally, because you need to compute these potentials, and then you need to take derivatives on the potentials to get the fields, and derivatives are not really you know, numerically convenient. Just because you need to know for a derivative at a single point, you need to know the value of the function's value even at neighboring points, right? That's not very convenient. So we really don't want to do that. We want to go directly from the currents to the fields, right? And that's the idea behind the dyadic Green's function. It's a Green's function which allows you to go directly from currents to fields rather than having to stop in the middle at potentials. And that's the topic for today. Okay, so essentially, it amounts to solving Maxwell's equations without potentials. Right? It's still useful to use potentials, and we'll see later in the class when we do waveguides and things like that, potentials can be quite useful. But for scattering and antenna problems, the dyadic Green's function formulation is more convenient, especially for numerical calculation, as we'll see today. Okay? All right, so let's get started. So we start with Maxwell's equations, Faraday's law. We're doing time harmonic Maxwell's equations, and we assume we are in a homogeneous medium or free space. Right? And we'll first consider the case where we have an electric current and no magnetic current. Later, we'll see the magnetic current case as well. Okay, so that's the Ampere's law. So since we don't want to do potentials, we want to find out what kind of wave equation or differential equation do the field satisfy. And that's pretty straightforward. All you need to do is you take H from this, substitute it in here, and that gives you curl of E minus k square E equal to I omega mu J. Okay, and this is known as the vector wave equation. Okay, this is a vector wave equation. Because it's a wave equation of some kind with a vector quantity E. Okay, so essentially what we need to do is we need to find a way to solve this equation such that from the current you can directly go to the field, right? How do you do that? So what quantity takes you from a vector to another vector, right? So to go from vector current to a vector field, we need a tensor, right? Sometimes, tensor or a matrix. It's kind of the same thing, really, right? And olden days, in earlier days, it used to be known as a dyad. The dyad is the specific kind of a matrix, I guess. It's not just any matrix, but the idea is the same. If you want to go from one vector to another vector, you essentially need to use some kind of a tensor or a matrix or a dyad. Okay, so what is a dyad? So I'll write it with two uh, bars. So it's written as product of two vectors, AB. Sometimes this is called an outer product, right? So writing the two vectors next to each other like that is kind of an abuse of notation, but this was the notation that was used for dyads, and that's kind of what we'll use just for historical reasons today. But the way to think about it is to think about it as a vector times another vector as an outer product. So if you think of vector A as a column vector, then vector B would be a row vector of the same size. And taking an outer product of these two vectors gives you a matrix, right? So another kind of notation, if you're familiar with sort of with a Bra and Ket notation in quantum mechanics, maybe it would be written like this, right? Or you can write it as a column times a row times a row, right? So that's kind of the idea behind this dyad quantity. Okay, so hopefully that makes sense. So essentially now that we have this dyad formulation where essentially we want to say that okay, dyad is what takes you from J to E, right? And this dyad is known as the dyadic Green's function, G, and it essentially takes you from current through a convolution integral. And this is what we saw for the scalar Green's function as well. Right? So scalar Green's function took you from current to potential, or charge distribution to potential, using a convolution integral. Right? That was the idea behind the Green's functions. And you can go back and watch that lecture if you want to review that. It was 2 lectures ago in EM12. But it's the same idea here. So essentially, you want to write the electric field. We'll see where this I omega mu factor comes in. Volume integral, the dyadic Green's function, which is a function of r comma r prime, similar to the Green's function, dotted with j prime dr prime. Okay, so intuitively, what's the picture? So I have some current distribution, J. There's a current everywhere, and everywhere it's a vector. It's a vector field. So what is this doing? Right? This is transforming each vector. Let me draw it as a straight line. So if I want to find my field at some location E, R, what this is doing is performing linear transformations on each current vector. Each of them is transformed by a Green's function, which is a matrix, right? It has to go, which takes this vector to this vector. So every vector is kind of transformed like that. And at this point, they're all added up, right? That's what the integral here corresponds to. So essentially, this transforms currents to fields locally, and then you sum up all those contributions, and that gives you the field at this location, right? That's what this integral means intuitively. So now we want to know what is this function that transforms currents to fields. And that's what we'll derive today. Okay. So the claim is that this Green's function, dyadic Green's function, r comma r prime, is nothing but the identity tensor or identity matrix plus 1 over k squared del del g of r comma r prime. Right? So note that this is also dyad now. So you can think of this as del times del transpose, right? So what is the del vector? It's dx, dy, dz. And then the del transpose is dx, dy, dz. So this is in Cartesian coordinates. You can do it in other coordinates as well. So what does this gives you? This gives you the Jacobian matrix, right? Xx, xy, z, yx, yy, yz, zx, zy, and zz. Right, so we did it in Cartesian coordinates, but you can do it in any coordinate system, doesn't matter. So today, actually, in the derivation, we won't make use of a specific coordinate system. We want to be coordinate system agnostic, right? So we'll just use kind of this tensor notation of del del. And I'll skip this transpose just to be consistent with existing dyadic literature. but it's really del times del transpose, okay? If you want to think about it as a matrix or a tensor. But just writing two vectors next to each other without a dot or a cross essentially means that that's a matrix quantity. Okay, so you have a matrix here, a matrix here. So that's why this is a matrix quantity. So that's the claim. We want to derive this, right? So no, I like to do proofs just because it completes the picture and there are no big gaps left over. So we look at the proof of this. So we'll derive it essentially. Okay, so to start our derivation, I should mention that this is the scalar Green's function, g. Okay, so this is nothing but e to the ik mod r minus r prime over ikr, which is what we saw earlier, ikr minus r prime. Right, since we already know that quantity, maybe we'll start from there. Right, so we know that g of r comma r prime satisfies the scalar wave equation. Right? Laplacian of g plus k square g equal to minus delta of r minus r prime. So we saw this 2 lectures ago. Okay, so we want to essentially use this fact. Before we do that, we can do one thing. So I said that E of R is I omega mu volume integral G of R comma R prime dotted with J of R prime dr prime. And we also have, so this is one integral that we have shown before, that this is what we want to get to, right? So we want to find essentially a function such that E can be written like this, right? So we actually start from this, this kind of expression. Yeah, and J can be written in a similar form as volume integral delta R minus R prime I dot J of R prime dr prime. Why can I write it like that? Identity times a vector is just the vector itself, right? So this is nothing but J of R prime. And of course, if I have J of R prime and I have a delta function in front of it, then this integral only fires when you have J equal to R, right? So on the left-hand side, you get J equal to R. So this is a matrix expansion or matrix, I shouldn't say matrix, it's just a way to represent J of R, right? An integral representation of J of R. The reason we do this is so that they look similar in form, right? This one and this one look the same, basically. Okay, so now what I'll do is I will substitute this and this into our vector wave equation from earlier, which is this one. Okay, and then what do you get? You get curl of I omega mu volume integral G dot J, should be a single bar, dr prime minus k square I omega mu volume integral G dot J dr prime is equal to I omega mu volume integral delta of R minus R prime I dot J dr prime. Okay, and that's the reason we had this delta of I, that's the reason we had I omega mu outside, because of this I omega mu, so we don't have to worry about it. You don't have to take it into the Green's function essentially. Okay, so now what do we have? We have this integral, this kind of equality. Okay, when R is not equal to R prime, right, then the Green's function doesn't have any singularities. So we're not integrating over any singularities then. Right, so if you don't have any integral over any singularities, then we can take this del cross inside the integral, because the volume integral is over R prime, whereas the del here is over R, right? Now you can't always do that and integrate a quantity inside an integral when you have singularities inside the integral, right? Because singularities can evaluate to a finite value, whereas the derivative of a singularity may not evaluate to a finite value, right? So you need to be a little bit careful about that. But since here, when r is not equal to r prime, you're kind of assuming that we're looking at points that are outside the source distribution. Then you can do this. Okay. Okay. So once I pull that integral in, you end up with you end up with the equality where now this quantity is in here, right? So essentially now you have the same thing everywhere. This quantity and this quantity are all the same. And since the v is arbitrary and j is also kind of arbitrary, it's true for all j distributions. That means that the arguments of these integrals must be equal. Right? And we've seen that we've seen this kind of an argument before. So we're making that same argument again. Right? So under that condition, we have that curl of g r comma r prime minus k square g r comma r prime equal to I delta of r minus r prime. Okay, and this is a tensor wave equation now, right? Because you have essentially tensor quantity, tensor quantity, tensor quantity, right? So you can think of it as three different vector wave equations where each column follows a vector wave equation and we put them side by side, or you can think of them as 9 scalar wave equations, right? Okay, so essentially we've shown that the Green's function we care about satisfies this vector wave equation, and we know the scalar wave equation is satisfied by the scalar Green's function. So we'll use these two facts to find out what this is and to establish our claim. Okay, so essentially what I'll do is we will start with the scalar wave equation and try to find a quantity that satisfies a vector wave equation like this, a tensor quantity. So we start with this. And then what I'll do is to make it a tensor, the simplest thing to do is to multiply on both sides with the identity matrix. A squared g equal to minus I. One way to think about this is that this is three different scalar wave equations that are all identical, which are the diagonal quantities of this tensor wave equation. And the other quantities of the tensor wave equation are all zeros anyways, right? So it's just three copies of this. Okay, so now what I can do is I can take this quantity inside. And also do it for the k. So this is still the same three different scalar wave equations. If I put the I inside, that doesn't matter, right? I can put a matrix here, and then each term on that diagonal becomes GGG. This one is GGG. And then it's like having three different scalar wave equations along those diagonals, right? Okay, and now I'll add and subtract a term to this. So we're going to add this dyadic term. And I'll also multiply on both sides with -1. I delta r minus r prime. So all I did is I multiplied -1 on both sides and I added and subtracted this term, a dyadic of G. So you can think of this as the Jacobian of G. Okay. So now what I can do is I can write this as del dot Ig. The same idea is that I have a matrix here and a matrix here. Now, obviously, this matrix times the identity matrix is nothing but the matrix itself. So this quantity is the same as this quantity, right? G minus K square Ig is equal to I delta R minus R prime. Okay? Now recall that we had a vector identity which was curl of A is equal to gradient of divergence of A minus vector Laplacian of A. Right? And we looked at this in lecture 0, I guess, when we did vector identities. So what you can do is you can actually extend this to tensors as well. A tensor would be nothing but gradient of divergence of A minus Laplacian of A tensor. So how do you interpret this? So if I take a vector, if I take a tensor quantity, you can treat it as actually three column vectors that are next to each other. And then when you multiply with the matrix on the left, it's the same thing as taking three different three vectors, multiplying by matrices and then lining them up next to each other. Okay, so you can essentially treat this as three different versions of this, right? And they're all lined up next to each other as three columns. Okay, another way to think about it is to think of this as a matrix, of course. The curl is also a matrix because the curl also takes a vector quantity to another vector quantity, right? In fact, you can write it in Cartesian coordinates. The curl matrix or the curl operator is nothing but 0 minus dx dy dz 0 minus dx minus dy dx and 0. Okay, so you apply this to any vector, f of x, x hat, f of y, y hat, f of z, z hat, and that will give you exactly the curl. Okay, so curl is also a matrix. So this is a matrix, this is a matrix, this is a matrix. Now on the right hand side, you have the divergence of a tensor, right? So what is the divergence of a tensor? You can think of it as the divergence of three vectors that are next to each other like that. Okay, or you can think of the divergence operator, which takes a vector to a scalar as a row vector, right? So if I have a vector and I multiply it by a row vector or a 1 by 3 matrix, then that will give me a scalar, right? So this is a 1 by 3 matrix, and this is a, let's say, 3 by 3 matrix. Then this whole quantity is a 1 by 3 matrix, right? And then the gradient operator takes a scalar to a vector. So that's a 3 by 1 matrix, right? So you have 3 by 1, and this whole thing is 1 by 3. So this whole thing is then 3 by 3. That's another vector. And it's the same thing with this as well. Okay? All right. So of course, vector Laplacian takes vector to another vector, and then tensor Laplacian takes a tensor to another tensor. So you can think of this as a matrix. All right. So since it follows a similar kind of expression, if you look back here, this is nothing but this, right? So we can write this as curl of Ig. Okay, so let's continue. Based on that, we have curl of Ig minus k square Ig minus dyadic of G equal to I delta R minus R prime. Okay, So now what I can do is I'll add a quantity to this. Curl of IG plus 1 over k square, curl of dyadic of G minus k square IG minus dyadic of G is equal to I delta R minus R prime. But what is this quantity? How can we just add this? The reason we can just add this is because this quantity is just 0. Why is it 0? You have a matrix here, you have a matrix here, you have a column vector and a row vector, right? So, of course, since they are kind of next to each other, you can multiply this matrix with this column vector. But we know that curl of gradient is 0. And you can check that for yourself. You can use this matrix for the curl. You can use a column vector for gradient, which is nothing but dx, dy, dz. And you'll see that when you do this product, they'll all cancel out. And you'll get 0 out here, a 0 vector. Okay? That's one way to prove that curl of gradient is 0 for any vector. Okay, so since that is 0, we can put that in there. Which means now what do you have? You have curl of I plus 1 over k square G minus k square I plus 1 over k square, G should be outside, G equal to I delta. And this completes the proof because this is exactly the tensor wave equation we wanted to get to. So this quantity here is our dyadic Green's function. And we've completed that proof. Okay, so we now have a dyadic Green's function, which is I plus 1 over k square del G of R comma R prime. And we know that E is I omega mu volume integral G dot J dr prime. Okay, so now that we know E, we can find H. We just use Faraday's law. So that's nothing but 1 over I omega mu curl of E. And then that's nothing but volume integral curl of G dot J dr prime. And this curl operator only acts on G, doesn't have to act on J because the curl is with respect to R, whereas J is a function of R prime. Right? Maybe I should write that out explicitly. So this curl operator is with respect to R. That's what that subscript means. You have R comma R prime dot J R prime dr prime. Okay, so in this entire derivation, we assume that Jm, there are no magnetic currents, equal to 0. Okay, but we can go back and do the same thing when we have Jm not equal to 0 and J equal to 0. Right? So if Jm is not equal to 0, J is equal to 0, then you will have Jm in your Faraday's law and J equal to 0, no J in Ampere's law, but you can go through the same thing because of the symmetries in those two equations, and that will give you H equal to I omega epsilon volume integral G of R comma R prime J of R prime dr prime, and E will be equal to 1 over minus I omega epsilon curl of H, and that is equal to minus of volume integral del r g of r comma r prime dot jm r prime dr prime. Okay, and the full solution when you have both of them is a superposition of both of these, this and this for E, and this for H. Okay, so maybe I should write that out. Right, using superposition, E would be I omega mu volume integral G dot J dr prime minus volume integral curl of G dot J dr prime, and H would be I omega epsilon volume integral G dot Jm dr prime plus volume integral curl of G dot J dr prime. Okay. All right. So if you go back and look at this G here, it still has these kind of derivatives in there, right? So we kind of started this by saying that computationally we would like to have only integrals, because integral is just a summation, which can be easily done using a for loop or with a vectorization. But we don't like to do derivatives, right? So we still have that. So we want to get rid of these derivatives. Okay, so to do that, we will actually have to evaluate gradient of G and find an explicit form for G which doesn't have these factors. So that's what we'll do next. Okay. So explicit forms of G. Okay, so this is just basically some calculus, nothing complicated. So we have G of R, capital R, is I plus 1 over k square del e to the ikr over 4 pi r, where r is nothing but modulus of r minus r prime. Okay, so to evaluate this, we need to calculate two things. First, we need to do the gradient of e to the ikr over 4 pi r, and then take another gradient of that, essentially. Okay, so what is this? So we can apply product rule, considering e to the ikr as one function, and then 1 over r as the other function. Or you can use, the quotient rule. E to the ikr is one and r is the other one. And we will use the quotient rule here. So we know that it's v du minus u dv over v squared, right? So v du minus u dv over v squared, and the 4 pi is just a constant. That's what we have. Okay, then we evaluate this, which is nothing but, so the gradient of e to the ikr is just ik times e to the ikr, right? If the gradient is with respect to r, capital R here. But we can use chain rule to do that, right? So it's e to the ikr times, it's ikr times e to the ikr, right? So the gradient brought down is ik. And from chain rule, you still have a gradient of r here, right? Minus e to the ikr, gradient of r divided by 4 pi r squared. So this is nothing but ik minus 1 over r e to the ikr over 4 pi r times the gradient of r. So it's a useful relationship to remember that the gradient of the scalar Green's function is this, right? But anyway, you don't have to remember it. You can easily derive it using product rule and chain rule. Okay, so we want to find another gradient of it, e to the ikr over 4 pi r, which means we need to take gradient of this term. And we can again use product rule with this as one term, this is the other term, and this is the other term. So you apply gradient one at a time, and you treat the other one as a quotient, right? So that is, so you take gradient of this. So I'll actually rewrite this a little bit just to make it a bit easier. So I don't have to use product rule and quotient rule separately. So I'll bring the R in there, and then it's a bit easier to just apply product rule, right? Okay, so now I apply product rule on each term at once, one at a time. So what is the gradient of this? So that is nothing but minus ik over r square times gradient of r. And gradient of 1 over r square is, or minus 1 over r square is plus 2 over r cubed. And that's just basic calculus times the same coefficient, e to the ikr over 4 pi gradient of r, and you have another gradient of r because of the chain rule, right? And then you will apply it to this term. So when I take gradient of this, it brings down the ik, and that multiplies with this coefficient, right? So I get basically minus k squared over r minus ik over r squared e to the ikr over 4 pi gradient of r, and another gradient of r again from the chain rule. And the last term is pretty trivial. It's just gradient of r, right? You have the same coefficient, minus 1 over r squared e to the ikr over 4 pi gradient of r. Okay. Okay, so we can kind of combine some terms, simplify this. I'm kind of skipping those simple algebra steps, but it's very easy to show that combining terms, you essentially get 2 minus 2 ikr minus k square r square over r square times gradient of r plus ik r square minus r over r square gradient of r, running out of space here, but I think I have just enough space. Okay. All right. So we still have some gradients to evaluate, but these are easy. We just need to find the gradient of r and the gradient of r, right? So del r is, so you can do it in a Cartesian coordinate system, x square plus y square plus z square. Right? This is equal to what? Square root function. So when you take the gradient, you get 1 over 2 times the square root function times the gradient of the internal quantity, which is 2x x hat plus 2y y hat plus 2z z hat. So that evaluates to nothing but 2r over 2 r vector over 2r. And then you can easily see that. So these two cancel out, and then you end up with r over r, which is nothing but r hat. And so it's kind of an interesting or important simple expression to remember that the gradient of r is nothing but r hat. And then you take the gradient of that, which you can apply again quotient rule to this expression. Okay. And that is nothing but u dv minus vdu minus u dv over v square r square. So this is 1 over r times gradient of r vector minus r hat gradient of scalar r. Right? Okay. So what is the gradient of R vector, right? This is equal to 1 over R. So R vector is x hat, y hat, z hat, right? So you take them one at a time and you'll see that that will come out to be the identity, right? Because I mean, you can think of the gradient operator as, so it's taking a scalar to a vector. Maybe we can do that. So the gradient operator takes a scalar to a vector. So that's a 3 by 1 matrix, right? Or yeah, 3 by 1 matrix. So this is dx, dy, dz. And my r vector on the right is a x hat, or I can just write it as xyz, right? So when I take this product, that gives me the identity matrix, right? Because dxx is 1, dxy, dxz is 0, 0, and so on. Okay, so right. So this gives me 1 over r times identity minus r hat, and we have a gradient of r, but we know gradient of r is nothing but another r hat, right? So that's r hat, r hat. Okay, and that's a dyadic quantity. Okay, so since we've evaluated these two things, we can now substitute them into this, and this, and then simplify. And that gives us essentially that gradient of e to the ikr over 4 pi r is e to the ikr over 4 pi r times 2 minus 2 ikr minus k square r square over r square r hat plus ikr square minus r over r square identity minus r hat over r. Again, this looks very complicated, but it's really simple, right? It's just an algebraic equation. There's no derivatives. There's just some coefficients and then some tensors, right? And the simple tensors r hat, and I. Okay, so since now we know what is this term, and we also know what is this term, we can substitute, actually we don't need this term, we only need the second term. We substitute that in here, and then evaluate this whole thing, and that comes out to be g of r comma r prime, or I'll just write it in terms of r. So here, g of r, which is the dyadic Green's function, is equal to 3 over k square r square minus 3i over kr minus 1 r hat plus 1 plus I over kr minus 1 over k square r square. So let me write this nicely. K square r square times I e to the ikr e to the ikr over 4 pi r. This way, so looks like a big expression, but it's really nice, right? Because it doesn't have any derivatives anymore. It's closed form solution and easy to program, as we'll see. Okay, so we computed the Green's function explicitly, but we also need the curl of the Green's function. right? And luckily for us, actually, that's not that complicated. We'll see why that is. So why is that, right? So if I want to evaluate the curl, the Green's function, I don't use this complicated form or this lengthy form. I can go back actually to the other expression, which was identity times 1 over k squared del del of g. So why is this? Because now if we take the curl inside, curl applies on this operator, on this dyadic. But we saw that curl of dyadic is equal to 0 because curl of gradient is 0. And we saw it earlier in the derivation as well. So this whole thing basically goes to 0. And now we get a nice simple form, which is curl of I G. Again, we have a vector identity of curl of a vector times a scalar. But we can also apply to tensors as we saw before. Vector identities can be extended and you will get this curl of I. Right? But curl of identity is 0. Identity is a constant. Every vector in the identity, every column vector is a constant vector. Curl of a constant vector is 0, right? So essentially that goes to 0. So you end up with something pretty simple, which is nothing but gradient of the scalar Green's function crossed with I. That's basically this. Yeah, but we know what the gradient of the scalar Green's function is. So maybe I should put my box a little bit later. Right, we just calculated that, which was ik minus 1 over r times e to the ikr over 4 pi r hat crossed with I. That's the curl of the scalar vector Green's function or dyadic Green's function, sorry. So this also gets a box. I don't like that box, let me do that again. Okay, so we've calculated explicit forms for the dyadic Green's function and its curl. So now we can put them back into the expressions for E and H and write the explicit forms of electric and magnetic field directly in terms of the currents. This is very nice because this is everywhere in free space. It's not a far field expression. So E, function of R, is I omega mu volume integral A of R hat dot J, R hat, as we had R hat dot J. So you only evaluate one of those R hats because that becomes a scalar, right? Plus B of R J e to the ikr over 4 pi r dr vector minus volume integral ik minus 1 over r e to the ikr over 4 pi r hat cross jm, right? Because here you had r hat cross identity dotted with jm. So that just becomes r hat dot jm plus jm. Yes, this is very nice because now you don't have any tensor quantities in here, right? They all got reduced to just some dot products and cross products. So that's one of the big advantages of using dyadic Green's functions is you can evaluate a simple integral like this without having to deal with the whole bunch of big terms that we saw when we were doing potentials and everything, right? So I can also write H similarly, H of R, I omega epsilon, and we'll see what A of R and B of R are, simple terms. So very similar here. R hat dot jm r hat plus b of r jm e to the ik r over 4 pi r dr prime plus volume integral k minus 1 over r e to the ik r over 4 pi r hat cross j dr prime. Okay, where a over r is 3 over k square r square minus 3i over kr minus 1. B of r is 1 plus I over kr minus 1 over k square r square. Okay. All right. So these are essentially all the expressions you need to calculate the electric and magnetic fields from a given current distribution of electric and magnetic currents everywhere, not just in free space. Right? The difficulty, of course, is in evaluating these integrals at the observation point, at the source point, where r goes to 0. So you get a singularity, and we'll see how to kind of handle that when we do method of moments. But essentially, yeah, as long as r is not equal to r prime, you can evaluate this integral easily numerically, because there are no derivatives in there. So you just compute each term, you do a vectorization or a for loop, and that gives you the electric field and the magnetic field. You don't have to evaluate both. You can just evaluate. No, actually, yeah, you do need to evaluate both. And you have a general case of J and J. Okay, so J and Jm can be given by field equivalence principle, which is sometimes known as Love's equivalence principle, right? But we introduced it as field equivalence. So J can be n hat cross h on the surface of a metal, or doesn't even have to be on the surface of a metal. It can be on the surface of any bounding structure, right? So if I have some bounding structure or some bounding surface, then I find J and Jm using field equivalence principle from the surface electric and magnetic fields. Once I know J and Jm, I put them into these integrals. These integrals are reduced to surface integrals then. Right? This becomes surface integral. And from that, you can calculate the fields everywhere outside. Right? You can also do this with dielectrics. So equivalent currents, if you remember, we did earlier. So we said that Jp, polarization current, is minus I omega epsilon naught, epsilon r minus 1 times E R, and Jm, which is the magnetization current, minus I omega mu naught, mu r minus 1, h of r. And then we showed that once you substitute these currents in place of the material, then you have free space everywhere, and you can use the free space Dyadic Green's function, which is what we just derived, to put these into integrals and then get the scattered fields. We'll see that in the next lecture when we discuss the extinction theorem, but that's the procedure to evaluate the fields. We use that to derive the integral equation. Okay, so one last thing is we want to see what happens in the far field. Okay, so in the far field, the Green's function becomes approximately equal to I minus r hat e to the ikr over 4 pi r times e to the minus ik r prime dot r hat. So why is that? So if you go back into this expression that we had here, so in the far field, we basically ignored these terms, which go as 1 over r squared and 1 over r cubed. Let me just check that again. That's right, because you have a 1 over r out here. So these terms go as 1 over r cubed, 1 over r squared. Similarly, these also we ignore. So you're essentially left with this, the identity. And also in the far field, r hat is approximately equal to r small r hat, right? And we saw that before, that the directions are about the same. And this r quantity, which is r minus r prime, we saw that this in the far field can be written as r minus r prime dot r hat. Right? When we did the far field expressions, and that's what those are the substitutions we made. Okay. Okay. So once you have this expression, then we can see what happens to those big integrals by substituting this. Oh, one more thing is, if you go back here, essentially that's like saying that a of r is equal to -1, right? And b of r is equal to 1. So we'll also make those approximations. So let me write that down. So a of r equal to -1, b of r equal to 1, r hat equal to r hat, and r equal to r minus r prime dot r hat. Those are the approximations. So under those approximations, the electric field becomes I omega mu volume integral j minus r small r hat dot j r hat e to the ik r minus r prime dot r hat divided by 4 pi r dr prime. Okay, so in the denominator, the capital R just becomes r, right? Because we saw that in the amplitude, we can also ignore this factor. Okay, but what is this? This I can write as j r hat dot r hat, which is just 1, minus r hat dot j r hat. This is actually nothing but minus j cross r hat cross r hat. Again, that's a vector identity of triple product, the triple cross product. You can show that easily. And then we also had a jm term, right? So this is something separate. It's the jm term, which is very simple because this jm term just reduces to, we can just ignore this, and then this becomes little r hat cross j. Right? Okay, so if you write it out fully, we get E. So actually this deserves its own space. If we have enough space, yeah, okay. So E R becomes minus I omega mu e to the ikr over 4 pi r volume integral j cross r hat e to the minus ik r prime dot r hat dr prime plus ik e to the ikr over 4 pi r volume integral jm cross r hat dr prime. And if you notice, this is exactly what we had when we found the far field expression in terms of the currents from potentials. Right? We could show that, we could simplify the expression for the potentials in the far field. And then for a point current source, we saw that in the far field, Hertzian dipole produces essentially this. And Hertzian dipole is nothing but the source for the Green's function, right? For a small dipole. And that's exactly what we got. So we are showing essentially that the Dyadic Green's function approach in the far field gives you exactly the same expression. And this is for the magnetic current. which is exactly the same or very similar to the magnetic field in terms of electric currents, right? Which would be minus I omega epsilon e to the ikr over 4 pi r volume integral cross r hat e to the minus ikr prime dot r hat dr prime minus ik e to the ikr over 4 pi r volume integral j cross r hat dr prime. Sorry, there should also be an e to the ikr factor here. So this should have e to the minus ik r prime dot r hat dr prime. And even in here, there should be minus e to the ik r prime dot r hat dr prime. Okay, and these are exactly what we had earlier. If you remember from Hertzian dipole, this was the current, right? So although we started this whole thing without using charge distributions, we only considered Faraday's law and Ampere's law, we ended up with the same expressions in the far field, right? So you could ask what happened to the charge distribution contribution. And that is implicit in the Green's function because we use that to calculate the scalar Green's function, and essentially that gets accounted for by the gauge condition, right? So even the charge distribution is involved in here. Implicitly in the current because the current and charge distribution satisfy the the Lorentz gauge condition, right? Okay, so that's kind of a technical detail, not that important. When we solve antenna problems, you only care about these currents. The charge distribution is implicit in there. Okay, so we've completed the field distribution in terms of the currents, both in the far field and in the near field. Basically, this is not just the near field, this is everywhere in space. And if you see this, basically, both the far field expression and the near field expression only have to evaluate one volume integral or one integral. So numerically, they're not that different in terms of computational load, right? Because once you calculate this term, you integrate over this, it's the same as whether you do it for this case or that case, right? So it's not really that different. Most of the computation goes into this volume integral calculation or the for loop or the vectorized version of this. So in HFSS, essentially, they evaluate these integrals everywhere in space, even in the far field. Okay, so we saw earlier in this class, I think after lecture 2 or so, how to extract the field distribution for a given antenna. So now what you can do is extract that field, use the field equivalence principle or Love's equivalence principle to find the surface currents. And then from the surface currents, you can find the fields everywhere outside the radiation box, right? And that's exactly what HFSS is doing. And now you know how it's doing that. So it's very useful to have, I would say, a code written out for these fields in terms of these currents. And maybe what I'll do after this is that I'll write out that code and provide it so that you can use it when you want to calculate the fields for a given current distribution. And that can be very useful for many problems in antennas, in scattering, and even in optics, right? Let's say you have an aperture distribution of a laser. So you know what or a fiber optic cable, you know what the field distribution is at the aperture of the fiber cable, and you want to know what the radiated field is. Right, and for many fibers or for many lasers, you typically are in the near field because the frequency is so high. Right, so you do need to use these near field expressions to calculate what the field is everywhere. So they're very useful to have in handy. Okay, so we'll end here. We've discussed quite a bit about Dyadic Green's functions. We did pretty rigorous derivations for every equation. What we'll do next is we will establish the extinction theorem, and that will be very useful to us in developing integral equations to solve for these currents. So we showed that once you have the current, you can find the fields using these expressions, but how do you actually find these currents? Right? For a simple thing like a dipole, you can approximate it as a cosine distribution, but for a very complicated antenna, you cannot do a cosine distribution, right? You have to find what the current distribution is. So That's what method of moments gives you, is that current distribution. And then once you have the current distribution, you can apply extinction theorem to then replace all the materials with free space, and then use the free space Dyadic-Green's function to find the fields everywhere. Okay, so we're kind of essentially building up our toolkit to do integral equations next, and that's what we'll continue with in the next lecture. Okay, so I'll stop here. I'll see you in the next one. Thank you.